Hi everyone, welcome back. This is lecture 2 of our multiplier hardware design series. In the first lecture, we covered a particular type of microarchitecture to design a generic binary unsigned multiplier. So the objective of this lecture is basically going to be optimizing our architecture 1, which we discussed in our previous lecture, and come up with the optimized architecture which uses less resources. So now let's get started. So this is the basic principle of a binary multiplication as we covered in our lecture 1 in details. And let's recall few points here from our architecture 1 discussion. Basically, we used 2n bit multiplier, multiplicand register. 2n bit multiplicand register we used there to basically hold the partial product values. Then n bit multiplier register we used and 2n bit accumulator register we used. So basically we used 5n registers, right? And another point is there we used 2n bit adder to basically add our multiplicand and our accumulator registers value. Okay, now our goal in this architecture is basically going to be reducing the number of registers. So now let's see how we can design a optimized architecture which use less number of registers and give the similar results. So this is the optimized architecture. So here basically we are going to use only n bit multiplicand register, n bit multiplier register, and n bit only accumulator register or product register. And we are also going to use only n bit adder here. So basically there is a lot of resource optimization here in this architecture. Okay, now let's discuss how this architecture is going to work. So here we have stored our multiplicand value to this multiplicand register, and this is our multiplier register which will get the multiplier values, and this is our n bit adder. Okay, so now let's see how it is going to work. So this control unit is basically going to check our Q0 value. So if our Q0 value is 1, this add signal will asserted, and this shift right signal is basically always going to assert for each values of our multiplier register. So if our Q0 value is 1, what we are going to do? We are going to add multiplicand and our accumulator register values, and the sum value we are going to store in this accumulator register back, and if there is any carry, that carry will get stored in our C register. And now in the next step what will happen? All these, the carry register, the accumulator register, and the multiplier register values will get shift right by 1 bit, such that the carry bit will basically come to MSB position of accumulator, and all the accumulator bits will get shifted right by 1 bit, and the LSB bit of accumulator will occupy the MSB bit of our multiplier register. Again, all the bit of multiplier will get shifted right by 1 bit, and this Q0 bit will be lost. So this is how this hardware is going to work, and the final product value is going to store in our accumulator and Q register together. So AQ is going to store our final product value. So for n bit multiplication we need a 2, and the product is going to be 2n bits. So ultimately we need 2n bits of the product. So the 2n bits of the product is basically going to be stored in our accumulator and Q register together. So this is how this architecture will work, and definitely it is optimized from a resource point of view. So here is the algorithm. On start we will check our Q0 bit. If Q0 bit is 1, the accumulator and multiplicand register will get added, and the result will back store into accumulator register, and if there is any carry, it will go into the carry register. And then the CAQ register will get shifted right by 1 bit, and this process will repeat for all the bits in our multiplier register, and once it is done, the final product value will be stored in A and Q. Okay, so these are the algorithm steps as we discussed. Multiplier and multiplicand bit will be loaded into Q and M register, and initially our accumulator will be initialized with 00. All bits will be 0, and the carry bit will also initialize with 0 in starting. So C is a 1 bit register which holds the carry bit resulting from the addition. If Q0 is 1, the multiplicand is added to the register A and stored back in register A and C bit used for carry. Then all the bits of CAQ are shifted to the right 1 bit, so that C goes to AN-1, A0 goes to QN-1, and Q0 is lost. Q0 is 0, that means no addition is performed, only shifting, right shifting by 1 bit will be performed. The process will repeat for all the bits of the original multiplier register, and the resulting 2 and bit product will be stored in AQ register. This is an example here. So again we are taking a multiplication example of 7 cross 7. So initially the carry register will get initialized with 0, accumulator will get initialized with 0, multiplicand register will get initialized with the multiplicand value, our multiplier will also get initialized with our multiplier value, and the count will set to 3. Count will be nothing but the bits in the number of bits in our multiplier register. And this is the initialization step. And in next step, what we are going to do, we are going to check our Q0 bit. So if Q0 bit is 1, what we are going to do, we are going to add our accumulator A and multiplicand M. So the 0 0 0 will get added with 1 1 1, and the result will be 1 1 1. The Q0 is 1 1 1 here, and here only our addition operation has performed. Now the next step will be shifting. So here initially the carry is 0, so the carry will get shifted to here. The LSB of accumulator will go to MSB of our multiplier register, and the count will get reduced by 1. So here the multiplicand is going to be same in all the steps, because there is no shifting and all is happening on our multiplicand register, so it will always hold the same value. Okay, in next step again we are going to check our Q0 bit. So Q0 bit is again 1 here. So if Q0 bit is again 1 here, then what we will do, we will again add this value, the new accumulator value, and the multiplicand value, which is 1 1 1. So the new result will be 0 1 0, and there will be carry this time here. Now in the next step we are going to shift. So this bit is going here and this is going here, and the count will be reduced by 1. Now in the next step we will again check our Q0. So Q0 is again 1. So if it is 1, then again the addition will take place, the accumulator and the multiplicand register addition. So 101 basically will get added with 111. That means new result will be 100, and again there is a carry this time, and this is nothing but our this value, and this is the operation AA plus M has happened here. And now the shifting will take place. So this bit will go here, 0 will go here, and our count will reduce to 0. Now since our count has reduced to 0, that means we have the multiplication operation has taken place completely, and the final product value is going to be stored in our accumulator A and our multiplier Q. So the final value is nothing but 110, then 001, which is nothing but in hexadecimal 31 and in decimal 49. So I hope this example is very much clear and how this algorithm works. So these are the observations. As we discussed, we need only n bit multiplicand register, n bit sum and product register, 1 bit carry register, and we need only n bit adder. So guys, if you are looking for quality VLSI related contents, you can visit my channel youtube.com/VLSI Excellence, where you can find lots of concepts related to Verilog SDL, static timing analysis, theory concept, as well as practice or interview questions. Then also on low power VLSI design concepts and practice problems are covered there, and as well as lots of other projects also I have covered.